Hello everyone, so Ikram, Abdelkefi, Clément, Fernandes, Wojciech, Pieczynski and I want to thank the scientific committee for inviting us to present our work on forecasting with pairwise Markov models. So the problem of the estimation of an unobserved process X by an observed one Y, it's often treated in the framework of hidden Markov models. The field of applications of hidden Markov models is extremely vast. We can quote, for example, image segmentation, signal recognition. This class of models are characterized by a good computational complexity and good results with few data. To deal with continuous data, a subclass of these models, named hidden Markov chains, have given interesting results in the past. So to begin, it is important to quote the well-known works of Clément, presented in 1960. More recently, many works on nonlinear and non-Gaussian filtering, like particle filtering, extending Kalman filter, with many applications in object tracking or time series, for example. So to begin, as an introduction, let's recall some definitions. So if we consider that X it's our hidden variable and Y the observed one, we can present our problem taking X and Y to discrete stochastic processes in R, and saying that the couple XY is an HMC, hidden Markov chain, if X is a Markov chain, and each Y at time n is independent to the entire vector X. So this definition can be illustrated by this equality. So the probability of the entire vector is equal to the probability of x anti-1 time a product of transition probabilities given by the Markov property and another product given by the independence property mentioned before. HMC are often described by their dependence graph. In our work, we use an extension of HMC, so the so-called PMC model. So PMC, pairwise Markov chain, extend HMC by only assuming that the couple is Markovian. So not necessarily X, but the couple XY is Markovian. And so writing this definition can be illustrated by this equality. So the probability of the entire vector is equal to the probability of our variable at time 1 time a product of the transition probability. PMC has also his dependence graph. So let's do some remarks. The first one is that HMC is a particular case of PMC, so we can have HMC taking having this equalities confirmed in the case of PMC. One of the most important things in this presentation to remember is that X in a PMC is not necessarily Markovian. The hidden process isn't necessarily Markovian. So PMC is more general than HMC. In many cases, PMC is better than HMC, filtering, smoothing, and our contribution in this work is to illustrate the fact that it's the same thing for forecasting. So I'll begin with a presentation of our model, a Gaussian stationary model. When I move on to computations for forecasting with our model, after that I'll do a brief comparison of the theoretical errors of our two models. Finally, I will talk about two forecasting applications on real data, the the applications on the prediction of atmospheric pressure and another experiments on soil moisture. So we can define our model, which is a particular case of PMC, a Gaussian stationary PMC, taking two variables, x and y, assuming that there are two Gaussian processes, taking value in R, with means equal to 0, variances equal to 1. So we are in a PMC framework, so Z is assumed to be a Markov chain. We have, by stationarity, the possibility to write the different covariances here as constants, and we can see that we can find our covariances in the dependency in the dependence graphs. So 2 remarks. From the stationarity, it is important to say that the entire distribution of our pairwise Markov chain is defined only by the beginning of the chain, defined by this covariance matrix, and we can find the HMC case, which is a subcase of PMC, taking these values for C, D, and E. So we can see that PMC is defined by 5 parameters. HMC is defined with only 2 parameters. We can take any values for our covariances as long as the covariance matrix is positive, definite, of course. So let's focus on another formulation of our model. So our model can be equivalently given by a linear relation. Our process at time n+1 is a linear combination of our process at time n and a Gaussian white noise. The two constants A and B are deterministic matrix obtained by the values of our covariances. And as I said, since HMC is a particular case of PMC, we can find our HMC formulation, the formulation for our HMC Gaussian stationary model, taking these values for covariances. So the aim of this work is to compare HMC and PMC when applied to the forecasting. So there are 2 main terms to compute. The first one is this conditional expectation. So the conditional expectation of x at time n+k, so a prediction at horizon k, on the vector y 1 to n. And so it is, by definition, the optimal prediction in the sense of mean squared error. And the second term is the mean squared error used to evaluate our models, and it is given by the covariances of the conditional law, which is a classic formulation of a Gaussian for a Gaussian process. It is important to remark that since we are in a stationary model, the covariance matrix of our variable z is constant over time. So to compute the first term, so the conditional expectation, we can use the law of total expectation here, of total probability, and then here use the Markovian property of our couple. And then seeing that we can write this part, this conditional expectation, as a function of xn, yn, we can write this function as a linear combination of xn and yn, and then obtain our prediction as a linear combination of a conditional expectation n, yn. It's a projection of on the space of yn, y1 to n. I don't describe the whole computation of the covariance matrix of the conditional law, but we can say that it is possible to do it thanks to this equality and the recursion which gave this entire relation. So, knowing now after having defined our model, we are now able to have the prediction and the MSE, mean squared error, which is the value of the covariant matrix. So knowing that the theoretical data has our PMC distribution, we can write the MSE for our HMC. So we can see that it is thanks to a kind of Pythagoras theorem, it's an orthogonal projection, the MSE of our HMC here, which is equal to the MSE of our PMC plus the expectation square the difference between our two expectations with two models. Here I present a plot of the variation of the MSE values for an horizon K increasing. So imposing these values, for example, for A and B, and taking C close to the HMC case, we can just have a kind of perturbation variation around the theoretical values for an HMC and see that for all values of the length of chain N, PMC can improve upon forecasting with HMC. In these cases, the maximum gain is around 10%. Another interesting thing to see is that PMC converge more slowly to the MSE of the stationary law. So maybe we can say that for prediction at the long horizon, PMC is a good choice. So we decided to apply our model to real data to see the behavior on a data which, by definition, don't necessarily follow our PMC distribution and compare to it to the HMC behavior. So we choose to predict atmospheric pressure and Solmeister by temperature, so two experiments. The data was very easy to get. It was on an open source meteorological data set. So it is early values taken over 2 years, from January 2021 to December 2022. We estimate the parameters, so the covariances on each month on the first year, and with values estimated on 1 month, we test on the same month on the successive year to see the behavior of the prediction. So data are standardized, and to prevent periodic temperature variations from polluting the forecast, we subtract the seasonal components from the temperature, Y. So I'm going to present some MSE values, standardized, and the results of the prediction on graphs. And I present it only from the month of January 2022 for different values of horizon K and different length on chain N. So for the first experiment, the hidden variable X is associated to the atmospheric pressure, and the observed one is Y, the temperature. So for this experiment, we obtain these values for covariances. Here for the results, we can say that we can see that PMC is quite better than HMC, and the intuition is confirmed. When K increases, MSE increases also, so it is more difficult to predict when horizon increases. Here we can see for the 4th week of January the prediction at an horizon of 48 hours, so 2 days. And we can say that we can recognize a sort of polluting because we can recognize the oscillations of the daily oscillations due to the daily oscillations of temperature, but which pollutes a little bit our prediction. The PMC is better, and we can say that it is the HMC is much more sensitive. The oscillations are much more important. For the second experiment, the hidden variable is associated to the soil moisture. The observed one is always the temperature. We obtain these values. In this case, it is more difficult to highlight a pattern for our MEC, but PMC is always better. And we can note some strange behavior in this case. When K increases, our prediction is better. So we are working on that to understand it. We have the idea, but it will be presented on a successive work to describe it. And for the second week of January, I present the prediction of the soil moisture at an horizon of 72 hours, so 3 days. In this case, we can see that clearly the PMC is better than HMC to predict the soil moisture. So as a conclusion, we can say that many works dealt with the comparison between PMC and HMC in filtering and in smoothing. We did that for forecasting. It was our contribution. We can also say that we tested our two models on real data, and the results confirmed the theoretical results we found. As perspective, we are working on more complex switching models, well adapted to non-stationary data, non-Gaussian data, for example, Laplace-Kalman filter. Thank you for your attention.